My name is Marcel Demmler, and today you will learn about ion beam technology and how it is used for manufacturing of sensors. Let me give you a quick overview about the next 40-50 minutes. At the beginning, I will just very briefly introduce scia systems, just 3 slides, and then going right into technology, right? Giving a quick overview what types of sensors are available, and then giving 5 examples how our systems or what our customers do with our systems. So what kind of sensors, what kind of specific process steps are done using our technology. Scia Systems is an equipment supplier, so we build advanced ion beam and plasma processing tools. Basically, our systems do etching, trimming, coating, and cleaning of certain parts. So we have partners worldwide, and most of the technology is developed in-house. So basically, all the key components, all the ion beam technology is developed by Scia Systems. We're actually a rather young company, founded in 2013, but we have been quite successful. So we started here in Chemnitz in Germany, as Paul said, about an hour to Dresden, and we are already 260 employees. So we have been growing steadily over the last years. Annual revenue is close to 100 million euro. Also this year, we will be in the same range, maybe a little bit higher. We have sales and service partners in 17 countries and already more than 100 customers worldwide, with more than 500 systems shipped. Most of our customers are in the area of MEMS and optics. I think there will be also 1 or 2 MEMS examples in the next 50 minutes, but the focus of that talk is in the sensor world. Who are our customers? So most of our customers do wafer processing. So different wafer fabs around the world doing mainly 150 and 200 millimeter wafer processing, and mostly in volume production. So the majority of our systems is running 24-hour, 7 days a week. We do have also a reasonable share on R&D, and sometimes, from R&D projects, also very interesting technologies for the industry could come up. We have also like a second market where we are active in optics manufacturing. Optics manufacturing for Scia Systems means a lot related to the EUV technology. So a lot of companies in the supply chain of ASML are our customers. So also we are doing very advanced coding and etching tools for that technology, for that market. So sensors. If I speak about sensors here, there are different types, and each one is using different physical principles. For example, proximity sensors. So how to measure distance. You could do it optically, you could do it with ultrasonic, or also magnetically. And each of those physical principles requires, of course, a different sensor design and different materials at the end. For pressure, it's the same. So usually you have like a membrane or something what is bending, and how to measure it, how much is it bending. You could measure it with piezoelectric materials or capacitive. Imaging, right? There are also different types, CMOS sensors, CCT. How to sense gas? Yeah, you could sense gas just with infrared light, so measuring the absorption of the infrared, or you use semi-absorption to measure it. Gyroscopes, so movement, how to measure that one? Very typical MEMS devices. Capacitive, piezoelectric, or also optical. And in my talk, I will point out one example of an optical gyroscope and how ion beam technology could be used there. Temperature, also a lot of ways how to measure temperature, like thermocouples with the Seebeck effect. You could use infrared cameras, or just the resistivity change of certain metals to detect temperature change. What is coming here for all those different sensor types and principles? You need a lot of different materials, sometimes complex multi-structures, like with different thicknesses, like maybe a few 100 nanometer to a few micrometer, right? If you speak about sensor devices like for the Internet of Things, so small devices. And which materials are used? Optical materials, of course, a lot of oxides, silicon dioxide, or dielectric layers like silicon nitride, also silicon, which is also optically transparent in the infrared, or other electro-optical materials like lithium niobate, lithium tantalate. Of course, if you want to sense magnetic fields, usually you need also magnetic materials within your sensors. Some sensors use platinum or gold as electrodes, or other materials as well. You have also the class of like transparent conductive oxides here, and the last one, piezoelectric materials, aluminum nitride, aluminum scandium nitride, PCT, zirconium oxide. And all those materials have to be deposited first, and then normally they have to be structured, they have to be etched. And the challenge now is that RIE is not working on many of those materials. Of course, like for silicon, silicon nitride, silicon dioxide, there are RIE etchers available, no problem to structure those. But for a lot of other materials, maybe platinum, PCT, lithium niobate, you cannot etch them with an RIE process. So ion beam etching is a good way to do it. On the right side, just an example, right? How such sensors could look like, many different materials in a stack, a mask on top, which could be photoresist or a hard mask. So our customers use both. Let me go right into the first example. Team R sensors. Before I go into the explanation what we do for Team R sensors, let me give you a brief introduction of ion beam etching. What is it about? So basically, ion beam etching is a physical sputter process. So we have ions with an energy of a few hundred electron volt hitting a surface, initiating a collision cascade, and then with some luck, one of those atoms is leaving the surface, and then this is called sputter process. And depending on the kind of ions, on the binding energy, and so on, the yield or the sputter rate is different. The big advantage compared to chemical etching is that that process is working on any kind of materials. If you can put this material into the vacuum, then we can do ion beam etching on it. It's working on rather low temperatures, so we have long mean-free paths, and also processing temperatures are relatively low. Just a clarification, because there are different types of ion beam etching or ion beam milling. So if we say ion beam milling or ion beam etching, typically it means we just use noble gases. It's a physical sputter process. There is also something called like reactive ion beam etching or chemical assisted ion beam etching, where additional reactive gases go into the ion beam source or just in the chamber close to the substrate in order to tune, for example, selectivities to get higher etch rates. In the following examples, I will focus only on this ion beam etching and ion beam milling. Usually you don't get a great selectivity for ion beam sputtering. So in the right graph here, basically we see like a lot of different elements, atomic numbers, and for argon it's shown how the sputter yield is changing. So carbon is etching very slow, and silver and gold are sputtering very fast. but most of the elements, they are basically in the same order of magnitude regarding etching rate. Just if we introduce chemistry, we can get a nice selectivity. Additionally, in our system, we have a substrate holder, which is able to rotate and to tilt. And this tilting allows us to change also the angle of incidence. This will be shown later how this could affect sputter yields. And there are some other positive side effects here. So TMR sensors. What is a TMR sensor? Thermomagnetoresistive resistance effect. So basically it means we have a very thin layer magnesium oxide, which is a tunnel barrier, and this tunnel probability of electrons to tunnel through this layer depends on the magnetic orientation of the layers on top and bottom of those magnetic layers. And if you want to use this as a sensor principle, basically this bottom layer is a hard magnetic material. It's pinned, it's not changing the magnetic direction. And this top layer is a soft magnetic material. So it easily changes the magnetic orientation in an external magnetic field. And that's the sensor principle now. So this TMR, so which is the relative change of the resistance here, is depending on the magnetic orientation. So if it's in the same direction for the top and bottom layer, or if it's in opposite direction. For opposite directions, we have a huge change in our resistivity, and that's the measurement principle now. So we have a lot of different materials. We have this oxide layer, we have as well magnetic materials, and even more. Now we have to make such a sensor. Difficult, right? So first, of course, one has to deposit all those materials, and here we see a sketch, a principle sketch of that sensor, and we have different materials. So first we have a mask on top. In that case, it's silicon dioxide, but could be also photoresist, for example. Then we have some metals, ruthenium tantalate, and ruthenium and tantalum. Some magnetic materials. Magnesium oxide is the tunnel barrier, and also the antiferromagnetic layer, this manganese-iridium. And if we want to etch through those layers with RIE, you would need for each layer, the wafer would need to go into a different chamber. If we use just argon ions, I showed that ion beam etching is working basically on any material. We can etch nicely through the layers. And we do this actually in 2 steps. So first step, we have an angle of incidence close to perpendicular, in that case 20 degree. In our system, we have a mass spectrometer connected. It's called secondary ion mass spectrometer. It's an endpoint detection system. So we are able to detect the elements which are etched at each point of time. So during the etching time, we will see what is etched, and let's have a look to this magnesium signal here. So once we are within that tiny thin 1 nanometer thick magnesium oxide layer, we can do something. We can control the process. And in that case, we'll tilt our substrate stage to 65 degree and continue etching. Why is that? Because we do physical sputtering, and the material, basically what is sputtered away here in that lower area, finally will go somewhere to the sputter shields of our chamber, but also to the sidewall here. And if we sputter metal here and we get a coating on our oxide layer here on the sidewall, there's a shortcut. So we would not be able to get any measurement signal anymore. So we have to make sure that that sidewall stays clean. And for that reason, this 2-step processing is very common for ion beam etching, to make sure that together with the wafer rotation, we don't have any redeposition here on the sidewall, and we have finally a nice sensor. The system we are using for such kind of processes is called scia Mil 200. It has a 350 millimeter ion beam source, but it's the big red device here, in order to etch a 200 millimeter wafer uniform, right, with about 1% or 2% non-uniformity. We have electrostatic chucks inside with wafer tilting, wafer rotation, and of course this endpoint detection. And in that graph, you see a system for volume production. It's a nice cluster tool. So 2 load logs, 3 process chambers, means we have relatively low, small footprint and can ensure also high productivity here. Yeah, let me come to the next example, infrared sensor manufacturing. Yeah, what is special about infrared sensors? So before I show you the process results, I want to explain one thing again. Why do we need, again, wafer tilting? So it's not just for the sidewall cleaning, what I explained for the TMR sensors. Yeah, it's also about controlling the sidewall angle. So if we have 2 processes, one with a perpendicular angle of incidence for our ions and one with 45, and then we do the etching, we would see that also the etching angle is different. So we can control also the sidewall angle here very nicely. And in the next example, that's actually needed, we don't want to have the 90 degree. Because we have one customer doing infrared sensors. So infrared sensors could be built out of lithium tantalate, which is a piezoelectric material. So temperature changes, you get a voltage. And in order to have very sensitive sensor elements, they have to have a low thermal capacity, so that those sensors need to be very thin. Lithium tantalate, you can't sputter it, right? You use a bare wafer, and then this one has to be thinned down by grinding and polishing. And our customer is doing it down to 25 micrometer. And if we would continue, then those wafers or those membranes could break easily. So the remaining 20 micrometer down to 5 micrometer are etched by, or removed by ion beam etching, which is shown here also on those SEM pictures. And why do we need a certain sidewall angle, not 90 degree? Because there needs to be also a metal electrode afterwards, where you can measure the voltage finally. And if this would be a 90 degree sidewall here, and you evaporate or sputter some metal on top, then maybe you don't have electrical contact. That's why a certain angle is needed here. And lithium tantalate, you can't etch it with RE, that's why ion beam etching is used. What else can we do? Ion beam etching is also used for the production of piezoelectric sensors. What is the piezoelectric effect? So we have a material with a certain crystal orientation here, maybe aluminum nitrate, maybe PCT. Top and bottom, we have an electrode. And if you apply some force here, then you would see that there is an electrical field. You could measure a voltage. You could use it also the opposite way. You could apply a voltage, and then you get some force, so some mechanical oscillation of this piezo layer. This strength of this piezoelectric effect is defined by a piezoelectric coefficient, basically, and there are different materials available, depending, of course, what you're making. So those piezoelectric effects, they are used, for example, for pressure sensors, accelerometers, ultrasonic transducers, or microphones. The materials which are common are PCT, with a very high piezoelectric coefficient, or aluminum nitride or aluminum scandium nitride, because PCT, you cannot use it in like CMOS fabs. So for those customers sensitive to certain materials, aluminum nitride is a material of choice. And the PCT, and especially the highly doped scandium aluminum nitride, they are difficult to etch with RE. So IBM is needed. If I say IBM, I don't mean the company IBM in the US. Not sure if they could help. It's ion beam milling. Yeah, let me give you some examples, and that you get also an idea about throughput here. So for PCT, we see here now a PCT layer covered with a photoresist, some platinum electrode underneath. And we etch this PCT layer with argon, or could be also other inert gases. And on the left graph, we plotted the etch rate of PCT and platinum. Yeah, let me. First, what you see, it's changing versus the angle of incidence. Second, it's about the same. Even so, at smaller angles, PCT is etching rather slow and platinum much faster. And if you go to higher angles, it's changing. So basically, we can tune the selectivity from lower to 1 to greater to 1 if it's about the PCT to platinum. For volume production, of course, one would choose a recipe with maybe like 45-degree angle of incidence, where we have a point here with reasonable high throughput. Photoresist, as mentioned, is no problem in our systems because we have a very effective vapor cooling, ion backside cooling contact together with electrostatic chucking. Yeah, let me. The other example I mentioned already, aluminum scandium nitride. So normal aluminum nitride, you use an ICP etcher to structure it. For the highly doped aluminum scandium nitride, it's getting difficult. So you might have some scandium residuals on your wafer. But argon ion beam etching, of course, is working fine. Also here we see a strong dependency on the angle of incidence. So as higher the angle here, as higher the sputter yield or the etch rate is. And as a reminder here, so angle of incidence, we just chilled our chuck in front of our big ion beam source. At the same time, we have wafer rotation, which ensures a very good uniformity. Let me take a quick turn to the magnetron sputtering before we come back to ion beam technology. Why magnetron sputtering? Because we have a really cool application here to use magnetron sputtering for making biosensors. Magnetron sputtering, what is it? I mean, I assume most people are aware of this technology. So we have a metal target mostly applying a voltage. Then there are some magnets behind. So we are able, with the magnetic field, to confine electrons, which leads to a higher plasma density. And this high plasma density together with the voltage, we can sputter. So it's the same sputter effect I just explained. So argon ions are hitting this target, and then material is sputtered off and finally deposited on a substrate. And the substrate itself could also rotate. There could be some translation movement. We could apply heating or also bias voltages to that one. Anyway, so in order to do biosensors, one can use so-called bulk acoustic wave resonators. So in that case, we see here a so-called F-bar, free bulk acoustic wave resonator, using the piezoelectric effect I just explained. So we have a piezoelectric material, aluminum nitride, electrodes, and top and bottom. And then you could apply a certain frequency, and the resonance frequency finally of your device depends, of course, on the mass of the device. Means if the mass is changing, frequency is changing, and frequency could be measured very easily. It's just counting, right? Frequency measurement. You can do it extremely precisely. And what our customers do, they put some chemicals here on top, some antibodies, and you could use it now to detect like certain proteins or maybe viruses within liquids. So you might put this sensor in a certain liquid or put a drop of blood on it. And if there's a certain virus within that blood, it will bound on those on the surface and finally change the mass of that resonator. How accurate is it? So the detection limit is about 10 picogram per milliliter, which is equivalent to a COVID-19 PCR test. So it's extremely accurate. But there are some challenges here. So if we speak about this aluminum nitride, this piezoelectric material, there are different ways to excite like a movement here. So different types of waves. There is a shear mode, which means the oscillation is in plane of this piezoelectric material, like left and right. And there is a longitudinal mode, just more like the, I would say, standard mode here, which is perpendicular to the plane. Yeah, now we have to put our sensor in a liquid. What happens? So if we look to the frequency, to the resonance frequencies of those two modes, and to the Q factor, which means, yeah, how sharp our resonance is, we see that in air we have a nice peak for the longitudinal and the shear mode, both. Now we put our sensor in water. What happens? That mode here, of course, oscillating perpendicular to the surface, gets a high damping. Yeah, it's moving against the water, so we don't have a nice peak anymore. So actually, that's not a very nice frequency where we would do measurements here. Yeah, because you see, it would move basically against the water. It gets a damping. And for the shear mode, it's in plane. You don't have such a strong damping. Still some damping, but not that strong. The challenge now for us as equipment manufacturer is we have to make an aluminum nitride, which is not excited in this longitudinal mode, but in the shear mode. How to do that? Yeah, we need a tilted crystal axis for the aluminum nitride. So in a normal sputter tool, I mean, the wafers like sitting under the magnetron, as I showed before, particles come more or less perpendicular to the surface, and also your z-axis would be perpendicular. And we need a tilted axis. So how to do it? First, we need a kind of rough buffer layer underneath, and then we have to make sure that our particles are basically coming from the side, not from the top. So the aluminum nitride atoms, they have to come from the side, and by that we are able to grow the aluminum nitride with a tilted crystal axis. How is this looking in reality now? We did a 140 nanometer of XSAN layer with about 30-degree tilt, which is a very nice angle to get a good shear mode here. On this picture, we see this tilted crystal structure for the aluminum nitride, and then some other layer underneath, like electrode and some other seed layers, in order to make sure that we get this nice crystal orientation. How do we know that the crystals are tilted? Of course, we see it here in the SEM, but we can do also in XRD. Here we have a pole figure showing us the crystal orientation, and there's right maximum here at 30 degrees. It's not super sharp, but we investigated it, and if there's no benefit if we make it much sharper, this peak. So that's a great result, and we see very nice preferred orientation for our aluminum nitride. So with those layers, one can build biosensors just activated in this shear mode. The tool doing that is a Magnetron sputter tool. It's an inline tool having some linear magnetrons and some wafer movement inside, including cassette loading, pre-cleaning, and also in situ thickness measurement. So also a tool designed for volume production. Anyway, let me come back to ion beam technology. Ion beam technology, I spoke so far just about ion beam etching, ion beam milling. There's a special case of ion beam etching, which is called ion beam trimming. So let me give you or start with one famous example first, because we just spoke about this Bohr resonator, which is used as a sensor device to detect biomolecules. Acoustic wave resonators or filters are in use of all of your mobile phones. And there are also filters inside which are trimmed or produced on Scia systems equipment. 100% sure. And such Bohr filters are obviously very sensitive to mass change. I just explained it. You can detect picograms of mass change. And that's a challenge for the manufacturing of such sensors. You have piezoelectric material, electrode, and also on top some passivation layer. But a typical sputter tool or PECVD tool, maybe you get 1% non-uniformity. And this 1% non-uniformity of thickness on a 200 millimeter wafer could easily yield to very low production yield. So actually, in order to make such Bohr wafers in volume production, you need well below maybe 0.1, 0.2% non-uniformity. Otherwise, your yield is very bad. So we can use a so-called ion beam trimming technology in order to improve this thickness non-uniformity for such Bohr devices. How is it done? So actually, each wafer gets pre-measured, and based on those measurement data from each wafer, the thickness uniformity, our system calculates how to scan with an ion beam. The ion beam has a size of about 1 centimeter, how to scan over the wafer in order to make it perfectly uniform, so as good as possible. This process is working, of course, on dielectric layers, also on metal layers. Just the measurement method, of course, for this layer thickness would be different. And we have customers using that technology for many, many different types of devices. So I mentioned already Bohr and SAW devices. There are thin film heads, and this will be on the next slide, because thin film heads for conventional read-write disk, they have like a TMR sensor inside. Already explained how to do it, and they have a write head. And there are also some challenges which have to be solved there, and ion beam technology can help. But of course, we can trim also a lot of other materials, also lithium niobate, lithium tantalate. We see also gaining interest there. So how could ion beam trimming help to make read-write heads for hard disks? On a hard disk or on a wafer where you make those heads for hard disks, there are thousands of those devices, of course. And for the right pole, basically it's a magnetic, some magnetic material. The size is just a few 10 nanometer, defining the right track here, and surrounding alumina matrix. And actually this is done by CMP. You CMP your wafer, and then you get that kind of shape. Unfortunately, CMP is not perfect. So on some areas on the wafer, you might see that this is still too thick, means the white pole is too wide, it's not small enough. On other areas on the wafer, it's already small enough. So we can use ion beam trimming in order to locally etch some material away on a 200 millimeter wafer to have all the right poles on the same thickness. Problem now, ion beam etching actually, the sputter yield is different for all the different materials. And if you look to that diagram here, how our etching rate is changing versus angle of incidence, we see that at 0 degree, so perpendicular angle of incidence, this magnetic material is etching 3 times faster than this alumina. It's actually not working. We don't want to create any step. But luckily, we are able to adjust also for that kind of tool, for the ion beam trimming tool. We can change the angle of incidence during our process. And there is a working point which has the selectivity of 1. And actually, this one is used in production. So we use it at 55 degrees. We can do this etching process and adjusting this white head thickness without creating any step here. One could use it also the opposite way. Maybe you have from your CMP some dishing and something like that. And if this is measured with an AFM, we could correct it also. All pre-calculated like this kind of step is different over the wafer. On each position, you have different step height. Then ion beam trimming could be used to correct the step height over the wafer. Just a reminder, again, why do we see this kind of change here in sputter rate or sputter yield? It's a normal physical effect. So imagine an ion is coming here under a certain angle. If the angle is smaller, at some point it's easier to release the atom. But if the angle is too small, then the ion would be reflected. So just a little bit physical background again. Why do we have those behaviors here? Here we have some real example from production. So we have a 200 millimeter wafer, some alumina on top. So that's the surrounding matrix I mentioned already. Different thickness, it has a certain thickness variation. It's about 1%, so not too bad, but not good enough for our customers. So they need much better. And we applied ion beam trimming and reduced the standard deviation here from 3 nanometer to 0.1 nanometer, factor 20 improvement here. Such a process on that 200 millimeter wafer with alumina. Alumina etches rather slow, takes 15 to 20 minutes. We have a lot of other customers where wafers need only 5 minutes, right, to get this very good non-uniformity. Of course, I have to mention the tool. What we have for that kind of technology, it's called scia Trim 200. We have a few hundred installations worldwide already, and it's used for film thickness correction, fully automated. Here we have a single chamber tool, Brooks handling robot, cassette loading, 25 wafers, and the process chamber. Yeah, basically wafer goes in, measurement data have to be fed in, and then the tool is doing the calculation and the software, how to process each wafer in order to make it perfectly uniform. Ion beam trimming is not only used for magnetic materials, it could be used also for photonic integrated circuits. Or actually it is, not just it could be. Yeah, quick slide, what are PIC? You know, photonics integrated circuits means that you integrate different optical components like lasers and of course waveguides, detectors on a wafer. Which types of sensors could be made with the help of PIC, biochips, LiDAR, environmental sensing, and optical gyroscopes. Yeah, and I will focus on the optical gyroscope because there are some challenges here. What is an optical gyroscope? So we have, yeah, imagine you have a waveguide on a wafer, like just the dimensions are tiny, right? And then on that waveguide, you have laser light, basically one is going clockwise and the other one is going counterclockwise. And then if your device is rotating, you would see that there is a phase difference between the two light signals, one going clockwise and one going counterclockwise. And actually, yeah, you just bring those lasers to interference, right? And then you can measure this phase shift. And this measurement is extremely precise. So you can measure up to 0.001 degree per second angular or velocity. The challenge now is that in order to make such good gyroscopes, you need extremely uniform waveguides. Uniform means regarding thickness. So you have a few 100 nanometer thick waveguide, and then you need maybe 1 nanometer non-uniformity. And that's sometimes difficult. If you don't get it right, you might have a phase shift due to a changing effective refractive index. Dispersion is changing if it's too thick. And of course, you want to have also just single mode operations for your laser, not multiple modes. So the dimension have to be controlled very precisely. Luckily, we just learned ion beam trimming could be used to correct dimensional variations on a wafer. Here I have an example usually for lithium tantalate. So for waveguides or photonics integrated circuits, different materials are used. Like silicon nitride, usually when you want to have very optical losses, the lithium tantalate or niobate, you can switch it electrically. So it makes it faster, but losses are maybe a little bit higher. So depending on the application, different materials are used. The challenge regarding the thickness is the same for all of them. So here we have an example. It's just a 100 millimeter wafer, lithium tantalate, with a certain non-uniformity. So we measured this lithium tantalate layer, which is bonded on a silicon wafer, by the way. It had a thickness before around 2.4 micrometer, and then we trimmed it down exactly to 1.6 micrometer, and standard deviation, and you see it here also on the graphs, is reduced significantly. Yeah, this is how it looks like after structuring. So this kind of trimming is done before you etch actually the waveguide. It's just on the bare wafer. The etching itself of the lithium niobate is done by ion beam etching, by the way, scia mill 200, what I explained before, because RE, lithium niobate, not working. Ion beam etching, it's a very effective and nice way to get nice clean sidewalls and good structures. Yeah, anyway, ion beam trimming is used for the thickness correction, and not only on the lithium niobate, also silicon nitride. So silicon nitride is also a very common material for photonics integrated circuits. Structuring done by RE, no need for ion beam, but uniformity is challenging. Yeah, even here, just maybe we have a look to those numbers here. You see thickness before we apply the trimming process is around 400 nanometer. 4 or 5 nanometer standard deviation means 1% non-uniformity. Yeah, it's not too bad, right? But we don't want to have like 1%, because this still means a couple of nanometers plus minus. We need plus minus 1 nanometer non-uniformity. And the only way to get it is to apply ion beam trimming. So we did this ion beam trimming process on a 200 millimeter wafer with silicon nitride. You see it here on those graphs very nicely. It's going to be very uniform. But maybe even more impressive on the histogram here. Here we see the thickness distribution. So before, maybe we have like 20 nanometer variation, and after plus minus 1 nanometer. Very impressive. And I mean, the theoretical resolution, basically one atom, it's an atomic process. What we can get, in reality, it depends a lot on the measurement accuracy, not too much on the tool. And also important, there's no change in roughness, there's no change in refractive index. So we keep the same material properties, just argon ion beam etching and removing some nanometers on top. Yeah, now I would like to come to my last example, how ion beam technology is used for making sensors. And this is now about ion beam sputter deposition. What is ion beam sputter deposition? I explained now multiple times about the sputter effect. So if ions hit a surface, material is removed, and this could be deposited on a sample. And ion beam sputtering means we use an ion beam from an ion beam source, etching material deposited on the sample. Usually you just use a metal target, and if you want to do oxides or nitrides, we add oxygen or nitrogen into the process. There is an additional cleaning ion beam source, which could be used for pre-cleaning of the substrate itself. What is the advantage of ion beam sputtering compared to magnetron sputtering? It's much more precise, it's very uniform, you get high density layer, you can control the properties nicely. Disadvantage, it's much slower, maybe 5 to 10 times slower compared to magnetron sputtering. Anyway, there's one big advantage. We can control the stoichiometry of certain layers very precisely. So we just have a metal target. In that case, we have some measurement data for tantalum pentoxide. And depending on the oxygen flow, what is shown here, we can tune the refractive index of our layer. Means it's going from fully oxidic to more like a metal mode. And this could be used in order to make vanadium oxide coatings, which are used as an infrared sensor. So one application is child presence detection sensors. This might become law at some point in Europe or in other parts in the world, that cars need to have sensors inside to make sure there's nobody left behind, no small children, no animals. When you close the door and the windows are closed, and in hot areas, this could be very dangerous. So this is one of the examples using it as infrared sensors. And basically you need a sensor material which has a very high temperature coefficient of resistivity. Means if the temperature of the sensor material is changing, you get a high resistivity change. So that's the sensor principle. And vanadium oxide is one of those candidates, but actually it's just in a certain phase. It's not like for VO2 or some other phase where you get these high properties. You need to have the right mixture, maybe adding also some other dopings. And we are able to control this very precisely with our scia code 200 system. Here we see some examples. Finally, we measure the resistivity of our vanadium oxide layer on a 200 millimeter wafer for a certain total resistivity is 1%, 0.3%. So it looks very good. And that's also reproducible, of course, in volume production. That's the main point here. With magnetron sputtering, that's difficult to control this poisoning of the target itself. The tool we are using, also available as well in volume production, as mentioned. Here we see a handling robot. That's the big Sputter ion beam source, designed for up to 200 millimeter wafers with tilting and rotating substrate holder. Also here on backside coating. Those tools could be combined also with other of our process chambers and clusters if needed. Now I am coming already to the end. I hope you learned a little bit about ion beam technology if you have not been familiar with that technology beforehand. So how is it working? What are the advantages of ion beam technologies? And what are the maybe big benefits for sensor materials? So in summary, the ion beam trimming, milling, and sputtering offer some unique capabilities if it's about etching or deposition of various materials, besides this conventional silicon or silicon dioxide. Of course, it's not competing with RAE if you want to etch silicon or silicon dioxide. But we are able to tune film thickness, density, stoichiometry, and by that, our customers can tune and optimize the sensor performance. All the systems are available in volume production, and here in Chemnitz, in our headquarters, we do have also a big demo lab, a lot of demo tours, so we are able to demonstrate all that technologies to our customers and to develop the recipes. Thank you for your attention.